Hello National 5, it's Mr. Neil here. In this video we're looking at computer systems, focusing in on data representation. So from the point of view of the SQA, this is what we need to know. To summarise, computers are used to store a variety of information. This is numbers, text, graphics, sounds and videos for starters. All data is stored in binary, as patterns made up of the digits 1 and 0. Computers only know two things because they're electronic circuits, and these electronic circuits can either be on or off, 1 or 0. Everything that you see on a computer is made up of these ones and zeros. At National 5, you need to know how the following are stored: positive whole numbers, real numbers, text and characters, and graphics. To that end, by the end of this video, you'll be able to explain how whole and decimal numbers are stored in a computer system. You'll be able to convert whole decimal numbers to from binary. You'll describe how text is represented in binary. And you'll be able to describe how vector and bitmap graphics are stored. Let's start in and look at whole numbers. So we are going to head on to the whiteboard and we are going to convert the number 168 to binary. To convert any number into binary, the first thing we do is write out our binary placeholdings, starting at 1 and doubling until we reach 128. The number that we are going to convert into binary is the number 168. The method that I like to use when converting numbers into binary is subtraction. So I'm going to subtract 128 from 168. This will leave the answer 40. That means that this calculation has been possible because it is 0 or more. So in that case, I'm going to write 1. I'm then going to carry the 40 and put it above the 64. I'm then going to subtract 64 from 40. That is going to give us a negative answer. Doesn't matter at this point what the negative answer is, but I can't have negative answers. So I'm going to put a 0. I'm then going to carry the 40 down again. And this time I'm going to subtract 32 from 40. And this will give me the answer 8. As this is positive, we're going to write down a 1. I'm then going to carry the 8 and put it above the 16. I'm now going to subtract 16 from 8. This gives us a negative answer. So that means I'm going to write down a 0. I'm going to carry the 8, I'll put it above the 8, and I'm going to subtract 8 from 8, which gives us the answer 0, so that calculation is possible, so I'm going to put down a 1. I've now got nothing left, so I'm going to add in the rest of the numbers as 0. That means the number 168 in decimal is equivalent to 1010100 in binary. So I've looked at how we convert a decimal number to binary. Let's now convert the binary number 0110010001 to decimal. Let's head to the whiteboard. To convert this number into decimal, the first thing we're going to do is we're going to put in our binary headings, starting at 1 and doubling till we reach 128. I am now going to highlight where the ones are. So we have got a 1 at 64, a 1 at 32, and a 1 at 4. We now need to add the placeholders where these ones are. So 64 plus 32 plus 4. When we add that up, we get the answer 100. Therefore, 01100100 is the binary equivalent for 100. So that's how we store whole numbers in binary and how we convert them back to decimal. Let's now look at how you store real numbers. And by real numbers, we mean numbers that have decimal points in it. For example, 3.1459. To store real numbers, a computer uses a system called floating point notation. If you're doing maths or physics, you may have also heard of scientific notation. It's very similar. A floating number is made up of a decimal fraction part called the mantissa and a power part called the exponent. So the mantissa is the number and the power is the exponent. Here it is in decimal form and here it is in binary form. The mantissa being the number, the exponent being the power of. Let's have a look at how we now store text. So to store text on the computer, we use a method called extended ASCII. ASCII stands for the American Standard for Information Interchange. And for each character that we have, there is an 8-bit binary code that represents that. That means we can store 256 different characters. These characters are control characters that we don't see on the screen, but they control the layout of the font. For example, we have the escape key. The printable characters are all characters that we see on the screen. So capital F is 70, lowercase r is 114. Above the number 128, we have all the special characters. These cover all your letters with accents for French, German and Spanish, etc. My name, Mr. Neil, in ASCII is 77, 114, 32, 78, 101, 105, 108. This is then converted to the binary equivalent of these numbers. What is your name in ASCII? Why don't you pause the video now and work it out? You could even work out the binary equivalent. Let's have a look at this question here. How many bits are required to store the following message in extended ASCII? So we've got the phrase Tom, Dick and Harry. To figure out the number of bits required to store Tom, Dick and Harry in extended ASCII, we need to count the characters. We need to count the letters within each name, the punctuation and the spaces. And then we need to times the number of characters by 8. So there are 18 characters, it's 8 bits per character, which means to store Tom, Dick and Harry in extended ASCII, we would need 144 bits. There are two main graphic types, bitmap graphics and vector graphics. Bitmap graphics store the details of every single individual pixel. Vector graphics store the instructions to draw the shapes that make up an object. Bitmap graphics will usually be for images, vector graphics for drawings and animations and cartoons style graphics. You can see here on the green apple that when I zoom in on the stalk, it becomes pixelated and I can see the individual pixels that make up the apple. Whereas on the red apple, because it's a vector, the instructions are scalable. So as I zoom in, it stretches instructions out so it looks realistically enough. Let's look at bitmap and vector in a little bit more detail. Here we have a simplistic bitmap graphic of a smile. There are two colours, black and white. We need to use 1 bit to store each colour. So for example, white is 0, black is 1. Using individual bits, I can store this whole image using zeros and ones. However, if I want to add more colour into this image, I need to use more bits. For example, the image on the left only has 2 colours because we're only using 1 bit per colour. The image on the right has 256 colours because we're using 8 bits per colour. However, the image on the right will take up more storage within the computer memory because for each pixel it's 8 bits, whereas on the left for each pixel it is 1 bit. We can also increase the quality of the image by increasing the resolution of it. And the resolution is the number of pixels within the image. So you can see the top image is a lot clearer than the bottom image because there's a lot more pixels. In a vector graphic, the properties of each object are stored. For example, the coordinates, the length, the width, the radius, or things like the fill colour, the border colour, and the border thickness. A really common vector graphic language is SVG, Scalable Vector Graphics, and there's an example of SVG code on the board there. Let's have a look at now how we draw different shapes in vector graphics. So there we have a red rectangle with a yellow outline. And in order to draw that rectangle, I need to know the X and Y coordinate for one of the corners. I then need to know the width of the rectangle and the height of the rectangle. And from that I get the full rectangle. I'm also telling it the fill colour, so it's shaded in red, the stroke colour, so it's got a border of yellow, and the stroke width, the thickness of the border. An ellipsis is just another word for a squished circle. We need to tell the computer where the centre of this ellipse is going to be, what the radius along the x-axis is, so from the centre point to the edge of the circle, and what the radius is on the y-axis is, so again from the centre up to the edge of the circle. And you can see again we've also specified a fill colour, a border colour and a border thickness. A polygon is a many-sided shape, so this could be a triangle, a square, a rectangle, an octagon, a hexagon, a dodecagon, any shape with many sides. And in order to draw an octagon, we have to specify the coordinates for each corner. We go round in a circular motion, specifying the coordinates, and then when the computer renders the image, it will match them up. Drawing a line in vector graphics is fairly straightforward. We have to specify the x and y coordinates for each end of the circle, and then the computer, when rendered, will match them up. In this video, I've outlined to you how whole decimal numbers, real numbers, text, vector graphics, and bitmap graphics are stored inside a computer.